It's my pleasure to welcome Ron Ho from Sun Labs. I guess it's Oracle Labs now, where he was a distinguished engineer. Ron started off at Intel, where he was a chip designer on the 486 and Pentium and Itanium, and he also worked on CAD tools at Intel. From there, he went to Stanford and got his PhD with Mark Horowitz. Many of you know Mark. And he was working on efficient and scalable on-chip interconnect. Ron joined Sun Labs in 2003, where he's been working ever since on interconnect both on-chip and off-chip. And that's what we're going to hear about today. So please welcome me and join me in welcoming Ron.
Well, thank you very much, Carl, for that introduction. I am delighted to be here this morning, or this afternoon. Coming here actually is in some sense a homecoming. Now, I've never been to the campus, but both my parents were undergraduates here where they met, fell in love, and got married. So were it not for this school, I would not be here today. So thanks for the introduction. I'd like to talk for the next hour or so about the work I've been doing at Sun Labs. Now, Sun Labs is now part of Oracle Corporation. They've kept the brand name of Sun Labs, but they changed most everything else, like job titles. But because it's work at Sun Labs, it is of course collaborative in nature, and so I owe a debt of acknowledgement to a lot of my coworkers. What I've tried to do in these slides is sort of distill some work over which I've had more of a leadership role, but where I talk about work that's done by others, I will point that out. All this stuff is of course public and open for public release. Now, I don't want to get too self-contemplative about this, but I'm clearly a product of my background. And my background, as Carl indicated, has been at Intel, Stanford, and Sun Labs. Now, at Intel, the one lesson you learn very clearly is whatever you make sure you can ship 40 million of them. And so you learn very quickly to become very conservative and really push on manufacturability. Now, I spent part of that time as a graduate student at Stanford. I was working half-time at Intel and full-time at Stanford. And as a graduate student, that couldn't be more diametrically opposed to what you'd like to do, because you want to be as crazy as you can be, push technology as far as you can, and try to graduate with that. And then when I graduated, I went to work at Sun Labs to work for Ivan Sutherland, and the lesson there was a nice amalgamation of the above, which is take some considered risks. Look at a roadblock you're going to hit in about 10 years and find a solution that's crazy enough to be interesting for research, but yet that you can manufacture. So I hope to show you information in some work here that is in fact fairly risky, yet manufacturable at the same time. And where I'd like to see the industry going is really in a notion of low-cost interconnect and what you can do with that, efficient computing systems, and how that's going to clash with resilience and a graceful tolerance to errors. But enough philosophy. The general context in which the work I've been doing falls into is this notion that our industry has had a great run. All right? This is performance of microprocessors over the last 25 years. I actually stole this data from Mark Horowitz. I added some more plots. I put Spark on top. But the whole thing is that this shows a 35% cumulative annual growth rate in performance. Now that's astonishing, right? So the natural question for computer builders, such as myself, is what can I do out, well, you can't see that. What can I do out to the right? Can I maintain this trend? Can I increase the trend? Am I going to be part of the generation that lets it fall down a bit? Will I choose to do that for other reasons like power? Well, if we think about performance, because this measures performance, we can go back to Hennessy-Patterson, chapter 1, crack it open, and it says that performance is really a metric of how many instructions I can execute per second. It's the wall clock time for a program. Okay, now instructions per second I can break into two parts. Instructions per cycle, cycles per second. More prosaically, I can call that parallelism and frequency. All right, so what does this tell us? Well, frequency, we've kind of hit a brick wall. If you go back to the 1994 Semiconductor Industry Roadmap, SIA roadmap, that one said that about now we should be at 25 gigahertz processors. Well, we're not. We're at 2 to 5 gigahertz, not quite 25. And that's because power really is a top-line constraint. We can't afford to pump the amps into a chip and pull the watts out the back. We just can't do that, and so power is limiting how fast we can run circuits. In addition, if I wanted to push frequency, I'd better get gate delays down, seconds per gate, and that's hard. And I better get gate per cycle down. Getting gates per cycle down means building what are called short-tick machines, machines that clock at 10 fan to the 4, 10 gate delays per cycle or faster. Now, I'm reminded that Michael Flynn at Stanford had this joke where he said, anybody who built an out-of-order machine never built another one. And the newer version of that is anybody who built a short-tick machine never built another one, because the design costs, the complexity is so large and so overwhelming that you don't want to be doing that. Okay, so that leads me to think, if I want to keep pushing performance and frequency's not going to get it from me, well, I better push even harder on parallelism. Okay, now all the architects in the audience, I hope you closed your ears for a second, because I'm going to gloss over the differences between instruction, task, thread-level parallelism. There's lots of parallelism that you can try to exploit. But for the purposes of technology, what I really care about is enabling parallelism means I have to have more stuff. I need more cores, I need more caches, I need more functional units, I need more switches. Caches are interesting. If I think about putting more cores in a chip, I need proportionately more memory than cores. If you think about it, if I take more cores, put them on a chip, and each core has the same amount of memory as it used to have, its miss rate is the same, which means the total number of misses for that larger block is going to grow with the number of cores, and that's going to swamp my chip bandwidth. Okay, so I need more stuff. I need more cores. I need disproportionately more memories. I need more switches. I need bigger chips. Now, Gordon Moore's self-fulfilling prophecy, not really a law, has done a good job to get us this integration over the past several decades, but, well, that's going to slow down because of economics. Right? We can't keep putting in exponentially more money into the industry to keep scaling our technologies as we have been doing because, well, there's a finite pool of money. Gordon Moore himself said, he said, any industry that relies on exponential growth will eventually find itself disappointed. It's a master of understatement. So we can't keep pushing Moore's law. We can't keep making infinitely large chips. Like the biggest chip that's sold right now as a microprocessor is Tukwila, which is named after a city near the airport, I assume. And that's 699 square millimeters. That's enormous. And the yield numbers on that are not very good economically. Actually, I'm sure whoever got it from 700 down to 699 got a nice bonus because kind of like I'd like to weigh 199, not 204, but it's nice to have that number. So we can't simply have big chips, and we can't simply aggregate chips together because then you're stuck with limited chip I/O. Okay, so I've got a rock and a hard place story. Frequency's not going to give me any benefit. Parallelism is hard to exploit because I need more and bigger chips, so what am I going to do? Well, we've had an idea at Sun Microsystems for a while now called proximity communication. This is an idea that was initially formulated by Ivan Sutherland about 10 years ago, and then Robert Drost and myself have been working very hard on the circuits ever since. The idea is quite simple. You have a chip, and the chip on its top layer of metal 10, metal 11, you draw a square. The square is 25 microns on the side. In fact, you draw a whole bunch of them, a nice array of squares. On a matching chip with a matching set of squares, you put them together. You don't solder them, you don't glue them, you just put them together. And by being in close proximity, I have made capacitors. Now, if I signal on one capacitor, that's going to make the other capacitor plate move in sympathy, and I get communication, albeit at a reduced voltage, but still I can magnify that and get data across chips. Now, what's interesting about this is, well, they're small structures. They're really small structures. The density of this bandwidth is easily 40 to 60 times more dense than area solder, C4 style solder, for example. They're small structures, so the power I consume to transmit data is relatively low. I can do 1 picojoule per bit, same thing as 1 milliwatt per gigabit per second, so it's relatively small energy costs. The systems that I can build out of this could potentially be very high yield, because if a chip is broken or doesn't work or fails, I just pick it up and put a new one on. They're not soldered, they're not glued. And I get essentially chip-to-chip communication that has the costs, the area, the power, the latency, that's very similar to being on chip wires. Okay, so why is this useful? Well, if I can have off-chip I/O that looks like on-chip wires, well, then I can imagine, okay, this is just a cartoon done in SketchUp, not a real chip, not a real system, but I can imagine a system made of lots of chips aggregated together with proximity I/O. So imagine I've got processors in the corners, I've got a stack of DRAM over here, maybe in the middle that's a switch of some sort. They're all face up on a cold plate, and then face down I drop these bridge chips. What's a bridge chip? A bridge chip is a chip that has proximity I/O on its edges and wires, on-chip wires that run across them. So I can get from this processor to this memory stack through this bridge chip, which has interconnections that are very inexpensive, just like they were on-chip wires, which really means I've made a virtual chip. I made a virtual chip out of many, many small chips, or even medium or large chips, and such that I can sort of fake generations of Moore's law scaling and mock up this large silicon system. What's even nicer is that I can do this and mix and match technologies. If I want memory, I'd really want DRAM. Right? I want a DRAM process. I don't want an SRAM process because that's not nearly as dense. It's 30 times less dense than DRAM. So I can mix and match a DRAM technology with a logic technology, maybe some sort of SIGI technology for other kind of wireless systems, and I can assemble these into one coherent whole. All right, well, that's an appealing story, but there's always a cost, right? What's hard about this? And what's hard about this is alignment. So I've got these pads on these two chips, right? Now, if the pads are aligned perfectly, I can communicate, but what if one chip gets hot, expands, or contracts from thermal differences? What if somebody walks by the computer system and sort of jumps and the whole thing shakes? What if you sneeze when you're next to the chassis? These things may move, and misalignment is in fact a 6-degree problem. There's misalignment in X, Y, and most perniciously Z, separation, because the plates get far apart. Or I can tilt in 3 different axes. So I better try to overcome that somehow. Now, I've got a slide in here that actually shows work from some colleagues of mine in San Diego, but I'm showing it here because it's just so cool. That says that, you can do some tricks with packaging to get us to very well aligned chips. So imagine you take a silicon chip and you expose a square of the raw silicon, and you dunk it in some solution that's an etchant, and the etchant will attack down to the 111 crystal plane. Okay? Well, when you dunk it in the solution, it's going to etch a perfectly inverted pyramidal structure. It's a self-terminating etch because you'll eventually just end at that thing because it's a selective etch of very high selectivity, and that makes for me a pyramid. Now, then you go out and you buy a sapphire sphere, which is used as a lens for fiber arrays. So they're cheap. They're like 8 to 10 cents a ball. And I put a ball in that pit. So I've got this snow-coned ball. So I take another chip with a matching pit, put them on top, and now they've locked. Now the precision of that locking is set by the lithographic accuracy of defining this hole. What's a masking step? That's submicron. So if you think about using some pretty interesting manufacturing techniques, we can get sort of submicron alignment of 2 chips at a very low cost. And in fact, we've explored doing this inside a foundry to make it high volume compatible for manufacturing. So I've done some work in sort of looking at how circuits get affected by this sort of etching, and that lets us do it from packaging. Now, if I didn't want to worry about sort of packaging step, what else could I do? We could certainly use circuits to get us some misalignment here, misalignment compensation. Now, let's imagine I've got 2 chips with pads on the chips, okay? And they're on top of each other and perfectly aligned. What happens if I misalign in a planar sense, so in X or in Y or in rotation? Well, suppose the transmit pads and the receive pads were not the same size. Suppose the transmit pads were actually made up of much smaller pads arrayed out appropriately. So let's pretend that these small pads were all transmit pads and the big pads were receive pads. When you put them together, the receive pads will cast a shadow on some set of the transmit pads. So by a clever selection and positioning of muxes, I can take the data that I'm trying to transmit to the chip and I can steer it to the right collection of micropads. Okay? So to do this, what do I need to do? I need to figure out what my misalignment is. I need to steer the data to the right place. And ideally, I would do this dynamically so that mechanical time constants being fairly long, I can do this every millisecond or so. Well, that's all pretty easy to do. So to measure capacitance, I can have a side channel off to the right and up to the top that has some Vernier structure that lets me measure the capacitance. I can do that with a fairly simple rectifying circuit. I can go over this offline if anybody has any questions, but it's a pretty simple circuit that lets us measure the capacitance very accurately. And then I need muxes distributed through here to steer data appropriately. Now, muxes tend to be expensive from a circuit perspective, so we can borrow some ideas from DRAMs and use bootstrap muxes to have only NMOS muxes that can still transmit the full voltage. Okay, so there's some circuit tricks that let me overcome planar misalignment, X, Y, and rotation. What about separation misalignment, or Z separation, or tilt, or yaw? Well, to do that, layout sort of helps you. So imagine that I've got 2 chips, and if I pull them apart, The problem really is that one chip can no longer see the matching pad on the other chip as clearly. Instead, you get defocused and you see all the pads around that other chip. All right, that's crosstalk. Now, if I do my pads differentially, so I have A and A bar, and I arrange them in this sort of butterfly-styled layout, then I'll argue that separation of the chips is not that big a deal, or it's mitigated by this layout because I can make any kind of coupling common mode, no longer differential mode. So imagine A and A bar are my bits I'm trying to communicate. And if I separate the two chips, inadvertently perhaps, trying to see A bar, I may actually see B and B bar also. But because they're arranged in such a way that they're equally contributing to noise, they have no net effect on my communication. Similarly for E and E bar. By the same token, D bar or D or C bar will couple equally to the bits I'm looking at, making differential mode noise now common mode noise. So with suitable common mode rejection ratio, I can make the coupling effects of separated chips to first order negligible. Now what this really means is I get some enhanced tolerance to chip separation. What we have measured is we can get for 25 micron pad sizes, we can get about 8 microns of separation. Now that's from the edge of the chip face to the other chip face. So once you add the passivation, it's actually more like 12 microns from the pad to pad, but that's a reasonable spacing for packaging to get you that close. Okay, so we can have this misalignment compensation both in planar and out of plane misalignment. The circuits themselves are relatively simple. Right? The whole point for this technology is the bandwidth density is so high that I do not have the need to overclock a few precious channels. So SerDes, serializers, deserializers, operate on the principle that pads are expensive. So if you want to use I/O channels, you better overclock them as much as possible because they cost so much to use and there's so much to make. Well, these are cheap. So I'd rather have lots of them and run them at, say, the system clock rate, which is much easier. And I can have circuits that are nothing more than a pair of inverters driving a capacitor plate. On the other side, there's nothing more than a strong arm latch. All right, so NMOS diff pair, cross-coupled inverters, and a clock for a tail device. Very simple. Now, I do have to worry about things like offset, and I have to worry about how I clock this guy. The way you clock this guy is, in fact, for every, say, 64 data bits, I'll have a side channel that's a clock channel that carries clock. And you can't have the clock channel be clocked because what would clock it? So the clock channel is a continuous time amplifier. All right, so very simple circuits. Now, if you look at this particular implementation, this requires DC balanced data, all right, because the capacitor does not send DC information. All right, so what's the voltage on the two nodes of the diff amp? Well, it's sort of undefined, and so we tie them through leaky PMOS devices to the power supply to bias them up at VDD. That means the data better be DC balanced and not give you a string of ones or zeros that's uncompensated. Now, I can avoid DC balance if I didn't want to do that, because that's an architectural cost you may not want to pay. I can do a refresh scheme where periodically I refresh these nodes and sort of halt communication temporarily. That's architecturally inconvenient often because now you have to shut the system down, but I can hide that by saying for every 64 data bits, I have a 65th channel that's refreshing. And I rotate which channel is refreshing periodically so the endpoints have no knowledge of this ever happening. By the way, please interrupt me if you have any questions as I go through this, or I'll just sort of keep going. All right, so the circuits are pretty simple. There are a few interesting challenges because it's all about capacitance, right? And these coupling capacitors are not very big. They're on the order of 8 to 10 femtofarads, which means any parasitic capacitance on the far side of the plate directly cuts voltage signal, right? That's not a very pleasant thing. So you've got to make sure that any kind of backplate capacitance is minimized. So metal fill, be wary of that. So make very clever metal fill patterns that don't increase the backplate capacitance. Noise, certainly by having clever layout, I can minimize or mitigate the effects of noise, but it's still there. So I better make sure that as I pull apart and lose focus, I have some sort of packaging scheme that prevents me from moving too far apart and having signal minus noise become zero. One thing you can do for this is offset compensation, but you got to be careful, because offset compensation often adds capacitance to the input of a sense amp, and any capacitance, of course, lowers your voltage swing. So there's a nice interplay of energy optimality and noise performance for these circuits. Okay, putting it all together, here's some work that I wasn't directly involved in but helped out on. If you have a lot of chips that are arrayed out in this proximity grid, okay, the question is, how do you put power in them? Well, you could solder them, of course, but once I've soldered them, I lose the argument that it's a high-yield system, because once they're soldered, I can't unsolder them. And so you have this known good die problem. Well, we've been working with Xerox PARC, Palo Alto Research Company, and they have this technology called, they call it claws. They're metal hooks on a substrate that when you do a sacrificial layer release, they curl up. And these hooks, shown over here, are very springy. You can push a chip onto them and they scrub into the pads and they make a nice conductive path of about 50 milliohms, pretty low resistance. They can do insertion cycles of hundreds of thousands of insertions before they lose their springiness. So, you know, we need like 10. And so we can think about taking substrates that have these claws on them, taking our array of chips and putting them onto that substrate. You get a nice temporary connection, the claws dig in, and you test them. You can test them at speed because you can deliver enough power through the claws, you can do that testing. If they don't work, well, you take that chip, you put another one in, and you keep going. You better be able to cool it because we're thinking of putting lots of chips into a relatively small space. So here's an example of a cooler on the right. It's actually sintered copper that has an inlet valve for water, outlet valve for hot water. And those structures can cool about 3 kilowatts, well, not that particular one, but from the same company, about 3 kilowatts on a 5 by 5 centimeter substrate, and that thing sells for under $200. So we have a lot of ancillary technologies that you can put around this communication system. But let's think of large-scale chips. Okay, what have we done? So we built a chip in 05. We talked about it at ISST in 07 that does, this is actually a relatively old chip. It was in a 180 nanometer technology, 1.8 volts. And it does 1 terabit per second per square millimeter of chip space. So it's a pretty efficient I/O channel. And you can't read this, but this is the RX and that's the TX. Those squares, that's the arrays of proximity communication. Relatively small. And it does, excuse me, 1 picojoule per bit, under 1 picojoule per bit for communication, and a latency that's relatively small and very low bit error rate. This is a contour plot of the I diagram at a certain bit error rate. I think this is 10 to the negative 12th, I'm not sure. And you can see that the I width is relatively good, about half a UI, and a few hundred millivolts of voltage margin. That's reasonable. What I like about this plot is this is the bit error rate as a function of chip separation. Okay, so if the chips are really close together, under about 8 to 9 microns, we see no errors. As we move them apart, we start to see errors because we're losing focus. And if we go out to 12 microns, it goes to hell in a handbasket because you just can't communicate over that distance. All right, so if I think about this technology, the next steps for doing this really is putting it into a product. We have a saying at Sun, now Oracle, technology transfer is a contact sport, so you really have to sort of get into the guts of product lines to deliver what you're going to see next, and I just can say stay tuned. But the whole notion of this technology really is, if you think about it, what have I done? I have turned off-chip wires into essentially on-chip wires. I've made the expensive, big, energy, power-hungry off-chip structures and made them on-chip wires. That's good because the bandwidth density of on-chip wires is quite nice, but if I think about on-chip wires, well, they're not terribly energy efficient themselves. The energy for an on-chip wire to swing is CV squared, right? Well, C is not going anywhere. 0.3 puffs per centimeter, and it's not scaling because that depends on the ratio of dimensions. And V is not really scaling much anymore because VT isn't scaling. So the on-chip wire power issue is one in which if I have more and more on-chip wires, I have more and more power. And I'm trying to make a system in which I have lots of on-chip wires. So the power scaling story for this for on-chip wires is not that attractive, and on-chip wires are also pretty slow. So what can I do about on-chip wires to make them faster? Can I think of other techniques to make on-chip wires equally as good or perhaps better than they were before? Well, the whole idea of proximity communication is you put a series capacitor to send data. So what if I tried that for wires? So the basic idea here is I've got a data stream on the left. It's going to go through an inverter. It's going to drive a long wire. But what if I put a coupling capacitor in series with the data stream? Right? That's kind of weird. If that series capacitor CC is about 1/10 the total capacitance on the rest of the line, that means that the swing on the wire is 1/10 the voltage swing. Well, gosh, that's reduced swing. That's low energy. And more importantly, I don't need a second power supply. So if you do low swing signals on a chip and you say, I want a 100 millivolt swing, and you go to the power supply designers and say, hey, can you give me a 100 millivolt power supply? And by the way, I need the impedance of that supply to be 1 milliohm. You're not going to get anywhere because that's just too expensive and it's sort of a non-starter. So this lets me do low swing signaling without requiring a second power supply. More interestingly, if I have the series capacitor, the load that the inverter sees is now significantly reduced. It's 1/10 the load that it would have seen before, so the driver gets real small. Now that's nice because now I don't have low energy in the wire and this big honking driver to drive it. The driver is also reduced in size. So net, I win in power for the entire system. In addition, that capacitor gives me a pre-emphasis kick because it's an AC short. So if I swing this voltage from 0 to 1 by this inverter, the node here will actually overshoot by quite a bit, pre-emphasis, or de-emphasis perhaps, making this rise a little faster. So it's a little bit faster and it's lower energy. All right, so that seems to be interesting. How do you make this circuit? Well, you need a capacitor. And one thing we did when we did this chip is to look at, well, what's a good linear capacitor that doesn't care about voltage bias? Well, you look at wires. A wire's capacitance is mostly side to side, no longer top to bottom, right? So I can make a capacitor out of interdigitated wires in a pitchfork scheme. Now, this is interesting because what I really care about is a ratio of this coupling capacitance to the wire capacitance. And this will track variations in wire capacitance. If I didn't care about that tracking so much, I could use multiple metal layers, of course. And at the end of this is an amplifier. And yeah, I don't show it here, but it's again a strong arm style sense amp. One benefit here is that the amplifier at the end can be relatively large because its capacitance is swamped by the wire capacitance, and so it can have relatively low offset. All right, so this all seems to make sense. We went and built a chip. This is back in 2005. It was a 180 nanometer technology, and we did up to 10 millimeters long wires, running about 1 gigahertz, and trying to get 50 millivolts of swing at the receiver. Now, if you do this, you better make sure you don't have noise issues, and so we twisted differential wires. This is an idea that's been known in telephony for only about 50 years, and so it's nothing profound, but we did do a twist of A and A bar and B bar. And if you twist them as shown this way, you can avoid Miller effect capacitance, which in fact saves you more power. The cost of a twist is relatively small. Here's a picture from our layout tool. We just did a 3D rotation, and it's just a few via pitches and another wire layer. In simulation, this is a plot of the performance versus the energy. So you want to live down to the right, sort of high performance, low energy. And if I'm driving a 1 centimeter long wire with a single driver, like a single stage repeater, I can vary the driver's size and trace out this curve, one repeater curve, in energy performance space. Not a lot of variation. If I use 2 drivers and broke it in half, I get a larger curve, so you probably want to live about here. But the capacitive driver was in fact quite a bit faster and a lot lower power. It lived down here. Okay? So in simulation, it seemed to be interesting. So we built a chip. Here's a die photo of the chip. And we showed about 10 times lower power and about 30% faster on repeated lines. For an unrepeated line, we actually showed a 3x boost that matched our simulations. Here's an example of that 1.5 centimeter unrepeated RC line measured on the chip with on-chip sampling oscilloscopes. And what you can see here is a nice pre-emphasis kick of a 00010 runt pulse data pattern. Okay, so we built this chip. It seemed reasonable. Well, then we said, hey, we can make some observations here. One thing is, if I send a data bit in a non-return to 0 format, 0, 1, 0, 1, then what I usually get is a nice fast rise followed by a slow tail. It's an RC circuit. Okay? So if I could do a return to 0 signal, so a upward pulse or a downward pulse, okay? If I could add the complexity of making it return to 0, I may be able to gain something. I'm able to run it faster, so I might have improved bandwidth as shown here, or perhaps better latency. The latency is better because my wires are already equalized. They just need to split. They don't need to cross first and then split. So if I can make it return to 0, which is more complicated, of course, I may reap a couple of benefits in performance. All right? Well, it turns out that if you use a capacitor to drive a wire, capacitors are great summing nodes. So I can sum voltages by simply adding together the outputs of the capacitors. So this gives me a chance to make a very inexpensive N-tap FIR filter. Here's a 3-tap filter that says that for a falling edge here, I could have a falling edge, a rising edge with perhaps twice the tap weight, twice the capacitance, and then another falling edge, which gives me that sort of two-mode pulse and the output of the wire. And in MATLAB, you can see that that actually gives you a nice return to zero pulse on an RC line. Okay? Well, that seems somewhat reasonable. If you look at this some more, what's nice is a 1 pulse is a rising, falling, rising stage. All right? So if I have a 1 followed by a 0, that means I have the pattern shown up here. So a rising, a falling, a rising. Well, what if we ran that system twice as fast? Just clocked it twice as fast. What that's going to do is it's going to overlap the second half of the first bit and the first half of the second bit for all pairs of bits. So if you look at this, it seems like what you can do is run it twice as fast, and when I have changing bits, I get double the preemphasis, which is what I need to run twice as fast. If I don't have changing bits, then I don't have double the preemphasis, but I didn't need it because, well, it's a hysteretic receiver, and I don't need to actually have twice the preemphasis. So this, if you sort of squint hard enough, you can call this adaptive preemphasis. That's a bit of a glorified term, but we built this chip and showed it at ISSC this year. In a 90 nanometer technology, 1 volt, we looked at conventional repeated wires and compared them with this notion of the return to zero signaling, either single data rate or this dual data rate system. We try to do it fairly so. In the middle here, you can see that the conventional repeated wires, we gave twice the pitch, twice the width, twice the spacing to give it sort of the same footprint. And the plot on the right, which I can't reach even if I jumped, is performance versus energy again. The pairs of points are the simulated versus measured for the chip that came back. And the black one on top are repeaters of standard conventional CMOS form. And the dots underneath are the versions that have the capacitive driver in red, the return to zero signaling in the middle, and the DDR version on the right. You can see that we have significantly more bandwidth for not that much more energy. So it's a reasonable trade-off that you could perform for these sorts of circuits. Once again, we had on-chip sampling oscilloscopes that let us look at the actual voltage in the wire. This is a plotted version of that where we had a 1 followed by a 0. You see the double preemphasis boost to make that 0 actually happen, followed by a 1. And that's what came out at the far end of the wire. Okay, so the notion really is that, take a step back. What have we talked about? We've talked about proximity communication that lets us have multiple chips tied together, in which the off-chip I/O is now made by on-chip wires. Number 2 is we made on-chip wires significantly better by using capacitors to drive the long RC interconnect for those long chip wires. So I can think of that as going hand in hand and enabling large compute systems of many, many chips tiled out. Okay, so the natural question is, what's the limit? What's going to keep me from tiling it out ad nauseum? So here are some cartoons. These are microprocessor pictures. Nothing real about this except that I drew it in a CAD tool that has, in this case, an 8x8 array or a 16x16 array of processors that are tiled with these bridge chips that are face down using proximity communication. And presumably all the on-chip wires have the capacitive drive, so they're efficient. But, well, this has a problem, right? Because now, to get from one processor, and some of these may be DRAM stacks, for example, to another chip in the system, I've got a latency that's now quite long. I'm looking at 20 centimeters, 30 centimeters to get across the system, and on-chip wires, I'm sorry, they're just kind of slow for that. So the limitation of the scalability of this really is that the latency of communication across this entire system is going to get too high. So what am I going to do about that? Well, we propose thinking about using optics for this. For such a large system, you can't get much faster than, well, the speed of light, right? So what if we had a system in which we had lasers coming in? I can modulate that laser, turn on and off with the CMOS driver. It goes into a waveguide running across this large system and goes into a receiver which I then receive using CMOS circuitry. That seems like it might be a good fit, because if I care about latency, well, light is about as good as I can do. If this is at all going to make sense, I better do at least 3 things. One is I better make the cost of this ridiculously small. I don't want to have this expensive at all. Number 2, I better try to separate any specialized optical processing, optical device, anything that's out of the ordinary from your standard logic or DRAM process, because you're not going to modify a DRAM process for photonics. And if at all possible, minimize the number of conversions from electrical to optical, just because they're going to cost energy. So to do that, we have this idea of something we call, sort of tongue-in-cheek, we call it a macro chip because it's bigger than a microchip. But if you think about what we have here, I've got a cartoon of multiple processors. Let's call them islands. Okay? And these could be processors, they could be DRAM, they could be whatever you want. And they're all face up, and they sit inside little holes etched into a silicon lattice plate that surrounds everything. Now, the silicon lattice plate is an SOI wafer that has waveguides drawn in it, waveguides that can carry and confine light. All right? And then face down, spanning both the lattice and the processor, or the memory, is a chip that does a conversion from electronics to optics and back to electronics. So the idea is we have circuits on this island chip that can communicate to this bridge chip, perhaps through fine-pitch solder, perhaps through proximity communication. And that data then becomes optical on this bridge chip, runs into a waveguide on the bridge chip, and the waveguide talks to this lattice and just transmits light back and forth. All right? If you can do this, then we can talk about transmitting data from one lattice point to another lattice point, another island, using purely optical communication and therefore the speed of light. Now to do this, of course, I need to make sure that I can get waveguides on this bridge chip to match up with waveguides on the lattice chip. We showed that at Group 4 Photonics, where we took a waveguide on one chip, for example, on this top chip, which is a bridge chip facing down. The waveguide terminates into an etched facet of the 111 silicon plane. That's 54.7 degrees. If you silver it, it becomes a mirror. So light hits this, bounces off, hits a matching mirror on the other substrate, boom, goes into a waveguide. We've got chip-to-chip communication optically. That's optical proximity I/O. We've shown that's about a dB of loss per chip, so it's relatively reasonable. Question in the back.
What happens about the defect rate on the wafer lattice?
I'm sorry, what happens
with the defect rate on the wafer lattice?
Right. So what's the question of the defect rate on the wafer? So my argument is that the wafer has nothing active on it. It's just passive waveguides, which are nothing more than silicon wires surrounded by silicon dioxide, and they're about 5 microns in size. So they're relatively large, relatively coarse. So yes, there will be a yield fallout from defects that are larger than that, but by and large, I have no transistors, I have no metallization, just photonic waveguides. And that's sort of key to the story here, because otherwise, this sucker would cost way too much. Okay, so we can talk about waveguides that couple from the lattice to the bridge chips, and the bridge chips that talk to the Cmos chips, or the memory chips, or the DRAM chips, and such that I can get communication through all of these. Now, this is really an attention focuser that let us promote circuits, and new devices. Because if you think about it, I've got to do optical modulators, I've got to do optical waveguides, I've got to do optical photodetectors, I need circuits to do all that. There's a lot of stuff that goes into the system. And so while we will probably never build one of these in the next couple of years, we're going to build all the parts that make up this macro chip. Now, it turns out that this is also a platform for thinking about some more system-level aspects. And so one question is, let's say I've got this lattice structure that has waveguides in it. Well, what kind of network would I like to make with those waveguides? Right? Should it be an arbitrated network? Should it be a standard mesh network that I go to my neighbors first before I go somewhere else? This is work that was done with my colleagues in Sun Labs Austin, in which we said, well, what's the right network? Now, it turns out that once we did all this work and submitted the paper, it became sort of painfully obvious that we should have seen the answer long ago. But what we've done is we've made the network, the bandwidth for this, incredibly cheap. Because I'm using WDM, which is wavelength division multiplexing. I can share multiple colors in the same waveguide. So adding another channel is cheap. It costs me 1/16 of a waveguide. It costs me one optical coupler, which is about 10 by 10 microns. They're very small. So what I've made inexpensive is bandwidth. And what is expensive are things like in-fabric routing, arbitration over many, many chips, sharing resources like that. So when you want to waste what's cheap and conserve what's expensive, that points you to making a network that is really a point-to-point, over-provisioned fixed network. And that was, in fact, the conclusion of the paper, which is going to be at ISCA this year, which says that if you have photonics, what you really want to do is avoid switching in the network. Do it at the site and make the network fixed point-to-point fixed bandwidth. Again, kind of an obvious conclusion once you realized it, but still interesting nonetheless. All right, so what have we done so far? This is a DARPA program. Actually, we're in year 2 of a 5-year program. The year 1 chip is shown right here. This is a 90 nanometer CMOS chip. It's a CMOS chip we built. We mounted on a printed circuit board. At the edge of the board, we wire bond and epoxy glob it. And on top of this CMOS chip, we then lay, boom, on top of it, an optical device chip. The optical device chip has waveguides, it has modulators, has receivers, and we talk to it with the fiber array. So here's our chip. This blue one is this chip right here. It's mounted on a PCB. On top of that, we drop an optics chip. We micro bump it. This is solder at about a 20 micron pitch, very fine pitch solder. So we can drive the modulator and the receiver devices on the optics chip, and fiber can bring light in and out of it. And we've talked about this at a couple conferences. And so what do we get? We got about 1 picojoule per bit for the transmit plus the receive. That doesn't include tuning power or laser power, but if you add those in, it's about 1.5, maybe 1.2. The transmit circuits are a 2-volt modulation swing on a ring modulator. And the receive circuits can do a sensitivity of negative 15 dBm. That's about 30 microwatts of received power. It's a relatively small signal that we can transform into a 1-volt swing. And a bit rate of no more than 10 to the negative 12. As an example of some of the work we did in a circuit sense, we can think about some of the components of this photonics link. So let's look at the receiver, because the receiver is kind of interesting. I've got an input on the circuit here from the left. That's coming from a photodiode. It's spitting out a very small amount of current. It's about 20 microamps average current, anywhere from 10 to 30 varying. And I've got to take that and change that current into a voltage at the outside. So that's done by a TIA, which is a transimpedance amplifier, because it turns I into V, so transimpedance, and it's becoming bigger, so it's amplifier. And I compare that small voltage with a reference to get my actual data. Okay? So there's lots of questions when you build a receiver like this. For example, what's my clock going to be like? Do I do phase alignment? Do I do frequency acquisition? What's the right structure for CDR? What's the power supply? Do I have to regulate that because I'm worried about noise in the power supply? Well, you do, in fact. What's the right structure for the TIA? There's a cascode, regulated cascode, a shunt-shunt. I've drawn a shunt-shunt here, but lots of architectural questions. Do I do offset cancellation on that? But rather than getting into all these questions, let me just focus on one question, which is sort of interesting, is how do I determine what VTH is? That's a threshold, right? I get a small voltage out of the TIA. I've got to compare it with a reference to say whether it was a 0 or a 1. So how do I pick the reference? Now, classically, for fiber line systems, the reference is often just an averaged version of all the data. It's the time averaged version of all your data bits running from 0 to 1, so that you can derive the threshold from your data. So that means that if my data moves up and down for common mode shifts, that's okay, because the average is still halfway between 0 and 1. Okay? So for any time I receive data, I just compare it with what the average has been, and that tells me whether it was really a 0 or 1. Now that's okay, but I need DC balanced data for that. Getting DC balanced data is somewhat expensive, because the traditional 8B, 10B encoding, which means for every byte you send, you pack it into a 10-bit stream so that you make sure that that 10-bit stream is almost DC balanced if possible. That's okay, but it costs you 25% more power because you're doing 10 bits instead of 8 bits. Other schemes are also not great because pathological data streams can cause large sequences of errors. So what can I do that's different from this averaging notion of VTH? Well, this macro chip is pretty small, so I can have a shared sense of time. So I could, in fact, say, hey, let's periodically reacquire VTH by saying to the entire system, stop, recalibrate, restart. Okay, well, we explored that path. And so what we did, and I wish I was much taller to actually point at this, but we had the input coming in from the left and I in. Maybe I can, you guys gave me a pointer, I might as well use it. So the input comes in here. Right? It's going to feed into a transimpedance amplifier, and that gives me a signal here. Well, I'm going to compare that with a threshold voltage, which I have fixed to be half VDD. Right? I've declared my threshold as half VDD. So I better make sure that my input swing is perfectly centered around half VDD. And I can do that by having this device right here steal away exactly the right amount of current to force the input to be centered around half VDD. And I can periodically recalibrate the system to make that true. Okay, now how do I do that? Well, one thing I can do is I could do an analog feedback loop and burn a lot of power and have a lot of complexity, Or I could do a digital circuit, which is what we actually did. We said, look, on the retraining sequence, let us first send a bunch of ones, right? All ones coming through. And so this is going to be a high value, okay? Now I'm going to use an integrator here and an adder and say that, well, I'm going to increase this bias current artificially to degrade a 1 value down to half. I'm going to force that 1 value down to the threshold point, okay? And I'm going to remember what that bias voltage was. So store that bias voltage that artificially dragged a 1 down to half. Next, I'm going to send all zeros. All right, and when I send all zeros, that's a low value, and then I'll reduce this bias so that zero is artificially pumped up to half. Okay, now I've got 2 bias settings. I have 1 bias setting that forced a 1 down, and 1 bias setting that forced a 0 up. So now I'll take the average of those 2 bias settings, and that will force a 1/2 to be at 1/2. And that forces the 0 and 1 to perfectly straddle b to d over 2. Okay? If there are any questions, I can go over this later because I did a very quick sequence of that. In fact, this is a picture of how this works, and I'm not going to go through this too much, but you can see that when you send a 1, I drag the bias down. When I send a 0, I drag the bias up, and I take the average in the middle, and that in fact sets my threshold to exactly the right spot. Now when I do this, I really need to make sure that I've got a good DAC in an integrator, because linearity is important, because I'm averaging a 0 and a 1 setting, and I want the middle part to be right in the middle for maximum noise immunity. Okay, what's the next step for us in Sun Labs? As I said, this is a multi-year DARPA-funded program, and those of you who've worked with DARPA know all about go, no-go milestones and all that sort of stuff. But we just hit our year 1 milestone, which is, well, last summer we did, which is 5 gigabits. That chip I showed you, 1 picojoule per bit. Year 2, we just taped the chip out about a month ago. It's going to hit 10 gigabits per second at 0.8 picojoule per bit for ARCs and TX and some tuning circuits. And eventually we're going to move to 15 gigabits per second at substantially lower energy, and that will be very exciting indeed. And there's a lot of interesting things to do in this program. Okay, so if I take sort of a broader view of the entire silicon industry, and you can split it any way you want. One way that I've sort of like to split it is I can think about high performance systems, whether it's in a laptop or a big iron installation of transaction processing. The notion of ubiquitous silicon and sensors and things that enhance sort of our everyday life experiences, car tire pressure monitoring systems and the like. Or silicon in sort of challenging environments. So human body, for example, space, rad-hard circuits. It doesn't care what the application really wants. They have different set points. But everybody wants to cut energy, right? You want to burn as little joules as possible. I want to cut the design time, the design cost, and not have to do specialized silicon design for every one of these applications. I want to have more and more rich communication, so better bandwidth. And I want to maintain resilience, some way to recover, hopefully gracefully, from any kind of errors, but not at the expense of one another. So one approach that's sort of outlined in the slides I've given really is, well, let's build systems through aggregation. I've talked about building very large-scale systems, but there's no need to build that if you didn't want. You could build a small-scale system in which I take components that are perfectly tailored to my application, tile them together, and connect them through a standardized interface like proximity I/O. Well, certainly I could break reticle boundaries and make things really big, or I could say, well, I'm just going to do assembly time configuration of the right mix of functional blocks. This is in some sense really sort of purposed reconfigurable computing. To do that, well, we have some ideas. We have this notion of capacitive coupling for this integration. We have on-chip wires that are more efficient and high performance. And if I really want to go to big scale, well, I can use optics. Or if I want to go to a fiber interface for really spanning large distances, I can do that as well. I think the good news is there's lots of open questions here, and especially in notions of the interplay of resilience and energy and some dynamic control over that. And certainly adaptive schemes will become increasingly important. Now, throughout this talk, I've had lots of cites for different publications, and here they are. I imagine I'm going to give these slides to Carl, and you can look at these later. But I'd be happy to take more questions at this point, and that's about all I've got prepared. So thank you for your time.
Questions?
So it seems like lately the problem we've got with chips is not having too little capacity, but too much. Multi-core, we don't know what to do with it. We don't know how to power it. How does that jive with the approach you've got of let's give you more silicon for one system?
Well, so one important limitation of large-scale systems that I didn't talk about is how do you program them? And I think that's certainly a valid question. It's not one we focused on so far. What I've really tried to do is focus on how do I get enabling technologies to assemble systems. I can go to large scale, although you have a very valid question of do I need that large scale? Or perhaps more importantly, I can have focused technologies for different applications. So I don't have to have lots and lots and lots of cores, but instead maybe what I really want is like 8 cores and a big stack of 16 gigabytes of DRAM right there. Well, I can enable that as well. And that is not a notion of giving myself lots and lots of more transistors that I might not be able to use, but rather retargeting the right kind of technology mixes for a particular application.
So I have a question about power. You're attacking, one of the things you're attacking with this interconnect work is power.
Right.
How much of the entire system power goes into the interconnect typically?
Well, that depends on the kind of benchmark you're running. So at least the optics program, so a lot of this is how do you respond to a DARPA BAA, right? For the optics program, the question really was, is there a system that we can really influence and change dramatically with the introduction of optics? And the target application for them was really GUPS, which is giga updates per second on a random access across the memory space. To do that really was an application of this called table toy random access, in which you have very small compute cores that don't do a lot except they read a bit of data, a 64-bit thing. They XOR it with something and they write it back. Okay, so for that application, the compute power is relatively small. The interconnect power was, I forgot the actual numbers, I want to say 2/3 of the system power. That one, you reduce the power using optics dramatically, you get a big payoff. Now, conversely, if you think about, say, I don't know, like Oracle, for example, right? The transaction processing for databases is going to have a much different performance profile. And I'm willing to bet that the interconnect is not the dominant part of that, all right? Unless you think about trying to fit data into a certain workspace. So the thing about Oracle databases, which is interesting, is that they have this concept of a hot set, which is any data you've touched in the last week. And that fits in like 64 gigabytes of memory for most of, for a large swath of their applications. And so trying to run those databases is hard because you're constantly swapping data back and forth to get that into memory. Now, for those applications, I would argue that going back and forth to disk is incredibly expensive. And being able to put that into memory is useful, and that would be a nice benefit for the interconnect, because I would then classify disk access as interconnect.
If you send 2 different signals through the same waveguide, would you see any intersymbol interference?
Not much, because what you really care about is what's the selectivity of the modulator and the wavelength the narrowness of that band for each channel. So we're talking in what's called the C band, which is a 1.5 micron band of wavelengths. And in there, you could break it into something like 16 different channels. And the communication of each channel in its particular color or its wavelength is narrow enough that we don't have any splosh over from one channel to the next. But that all depends on how good your optical devices are and what its selectivity for that frequency is. We're using resonant rings for our modulators, and they're very selective. In fact, you could say they're too selective because they're temperature sensitive. So you've got to keep tuning them, or you lose the resonant features of them entirely.
So you talk about the capacitive coupling. Can you also do the inductive coupling?
Right. I'm sorry, I'm not repeating the question. So the question, can we do inductive coupling in addition to capacitive coupling? The answer is you certainly can. And I've got a good friend of mine, Professor Kuroda at Keio University in Japan, has been doing inductive coupling for quite a while. What inductive coupling is just like capacitive coupling, except uses magnetic fields. And they're both pretty good technologies. I believe capacitive coupling gives you better noise performance because inductive coupling loops tend to be big, right? You tend to have magnetic fields that sort of circle what you've got, which means you better separate your channels by quite a bit, or they'll talk to each other. Now, one thing the folks at Japan do is they thin the chips down so that the so-called aspect ratio, the difference between the loops versus the loop size, is relatively small. It's like a factor of 1. So for certain applications, inductive coupling makes a lot of sense. For what stuff that I'm doing, I'd rather go out. I think building up is tough to get thermal solutions solved. How do you get the current and how do you get the heat out? I'd rather build out. And for those applications, I think capacitive coupling makes more sense. But there's a nice interplay there.
Okay, I'll suggest that further questions come down and talk to Ron. Thank you very much, Ron.
Thank you very much.